Hello everyone, welcome to the new section, and in this section we are going to learn about TF IDF, that is the first attempt at converting text into vector. And the interesting thing is that we are going to arrive at TF IDF very intuitively. Rather than learning any math, we will intuitively derive all the math that is necessary. So first of all, before even going into developing any algorithms, let's on a high level understand what is the need to convert text to vector, because we as humans, if we read this plot of Batman Begins, we kind of understand what are the names that are mentioned and other things. And let's say if we are shown similar movie plots, we can identify which of them are similar to each other, etc. based on, it could be sentiment or based on similar keywords, etc. But how does a computer do that? Simply, computer does not understand text. Everything has to be numbers. So when I mean converting text to vector, essentially text could be a single word, a sentence, or a collection of paragraphs like plot in our case. Everything can be converted into a vector. The beauty is that when everything is converted into vector, we can do mathematical operations to find similar vectors, etc. So you can easily find what are the similar movie plots to a given movie plot and other things. First of all, a lot of beginners do not really understand what do I mean when I say the word vector. A vector is nothing but a collection of numbers. It's just like a list or array, and usually text is converted into vector of dimensions, let's say 364, 768, 1024, etc. But what's the big deal about converting into vector, and what is this n dimensional number? Simply just think about n being 2 dimension. So a 2-dimensional vector is nothing but a 2D point. So if you take a 2D grid like this, here I have 3 texts with their corresponding vectors, and pizza is just a 2-dimensional number. So here a vector is just 2-dimensional, 0.5 and 0.5, and burger is 0.85 and 0.96, as you can see, and car is 0.75 and 0.1. So if you are able to convert any word, sentence, or movie plot into a vector, what happens is that now you can easily see from this diagram that pizza and burger are close together in the 2-dimensional space, and car is farther away. Similarly, let's say if you have 10,000 movie plots, you can see which movie plots are closer together, you can cluster them, etc. Just imagine this 2D grid, and similarly, instead of 2 numbers here, you might have 364 or 768 or 1024 numbers. Simply a similar comparison could be done in any n-dimensional space, not just 2D. Just imagine 3D version of this or any higher dimensional version of this, for example 768 dimensions. At the end of the day, all we are doing is comparing these 2 vectors with each other, whatever the dimension be it, and we can do cosine similarity, etc., through which we can know which vectors are closer together or which vectors are farther from each other, etc. And this is just a sample of how the 768 dimensional vector looks like. Essentially, everything is a floating point value between -1 and 1, and it's just a collection or list of 768 dimensional vector. 768 is a popular dimension that we'll encounter when converting text to vector using modern algorithms like transformers, etc. But nevertheless, what I want you to understand is, at the end of the day, n-dimensional vector is something just like this. Here n is 2. Similarly, you can extend it to any number of dimensions. And here I am just showcasing a word but you can assume that similarly a sentence or a paragraph or a collection of paragraphs, for example movie plot, everything could be converted into one single vector of n dimensions. And this is the holy grail of NLP, where we can convert any text, sentence or collection of paragraphs into a single vector, because now we can do all the mathematical operations like addition, subtraction of vectors, or finding nearby vectors in the vector space, doing clustering and all these things. So that's where the magic happens once you're able to convert any text or sentence or a paragraph into a vector. That's why we heavily focus on vectors. Great. With that understanding, let's take our first attempt at converting some text into a vector. So here, instead of taking 4 movie plots, I'm just taking 4 sentences. So, but essentially the method is same, how you are going to convert it into vector. Just for simplicity, I have 4 sentences, and you can just imagine each sentence could be just the whole movie plot text of Batman Begins, and second one could be Dark Knight, etc. At the end of the day, just assume that each of this is a document, each sentence is document in itself. Now let's take the first sentence, and immediately when we think about vectorizing it, what is the first thing that we get to our mind is actually dividing this sentence into its subtokens. For example, in this case, we are just splitting it by space, and you have almost 6 words. Ramsri is teaching an NLP course. Now you can create 6 columns. Each column corresponds to unique word that's present in the first sentence. And what is the simple thing that you can do is count how many times that word occurs and divide by the total number of words that we have. So here we have 6 words, and Ramsri comes 1 time, ease is 1 time, teaching NLP course, etc. So if you just divide 1 by 6, that's 0.166. So the simplest representation, the basic fundamental representation of this sentence into a vector is this, where you have columns that are individual words, unique words from this sentence, and you're just capturing the normalized frequency of that word. Nothing too complex, just the number of times that word comes in this sentence divide by the total number of words in there. So this is our first attempt at converting sentence 1 to vector. Now what we can do is, words like is, and all these do not carry much information. So these can be considered as stop words, and perhaps in this case we can remove them. But one thing to remember is that when we get to advanced algorithms like using transformer based modules, etc., even stop words are necessary and you need not remove them. But for simplicity, whichever words don't carry much information, we can just remove them so that we can make this concise. So if we just do that, what happens is that we eliminated is and an, but still we are capturing the relative frequency as it is. So we are dividing by the total number of words itself. And simply here we are taking 1 word. That's why we have 4. But the other thing is that you can take 2 words in combination, etc., or 3 words in combination and overlapping and other things, and frame similar columns like this. That's called as n-gram. So if you just take 1 word, it's 1 gram. If you take overlapping consecutive 2 words, Ramsri is teaching an, that's called a bigram. And if you take 3 words, Ramsri is teaching an NLP course, they are called as trigrams. So these are called as n-grams for simplicity. And just to make things easier for us, we are just considering just one word, that is 1 gram. But when you go to the coming sections, you can give what is the n-gram that you want to capture in the algorithms when you're forming these vectors. Anyways, now still we are at the conversion of this first sentence into vector, and we have just removed some frequently occurring words that we called as stop words, and we just got this as the vector. Essentially, this sentence can be replaced with a list of 4 numbers where each number is 0.166, and you know the corresponding columns or the features corresponding to this. So simply this could be represented into a 4-value vector. Moving further, our goal is not to convert just first sentence into a vector. Rather, we want to create a uniform vector that represents any sentence that you take. So in order to get uniformity, what you need to do is, instead of just keeping only the unique words that you get in one sentence or one document, take the collection of all the sentences, all the documents, and get all the unique words and create them as the features. So here, if you see, in order to obtain uniformity, where we want to represent every sentence or every document into a uniform vector of fixed length, we are taking this approach where we are creating columns of all the words, all the unique words that occur in this collection of documents or collection of sentences, otherwise also known as corpus. Remember, this word corpus simply means all the collection of documents or sentences, whatever it is. A corpus is just a collection of everything. So now if you go back, how do you represent your first sentence into a uniform vector? First of all, you fix the columns with all the unique words that occur in the whole corpus, that is the collection, which is Ramsey Teaching NLP Course, Mark, Computer Vision, JSON. And in order to represent the first sentence into a vector, all you do is go and simply fill in just those values that are present in first sentence. So only these 4 words are present in first sentence. That's why I am just collecting the frequency of those 4 words. Now what is the vector corresponding to 1? It is these 1, 2, 3, 4, 5, 6, 7, 8. Now you have an 8 valued vector that represents 1. Similarly, you have an 8 valued vector for every sentence. For example, let's take 4th sentence. Now these words Ramsey NLP are not present, so they are 0. And 4th sentence has 7 words. So each word JSON is 1 by 7, so 0.142, that's the frequency of it. And if you take this list of 7 numbers that you have here, that represents the vector for sentence 4. And the interesting thing is that this thing, the value is called as term frequency. Why is it called as term frequency? Is simply, if you take any term, you are just calculating how frequent that term is within that sentence or within the document. For example, for Batman Begins, let's say you have the plot of Batman Begins, and if you just collect how many times the word Batman comes in the plot, maybe 20 times it comes in the plot and there are about 500 words, then what is the term frequency? Just like how we have here 1 by 6, 20 times the frequency of the word divided by the total number of words, 20 by 500 is the term frequency of Batman in the Batman movie plot. Similarly, for every unique word in the corpus, you will just create a vector where you will fill in the term frequency of that column or feature. That's it. Term frequency is nothing but how frequent a word is in a document, the relative ratio compared to the total number of words. Now moving further, what else can we collect? For example, in the first sentence we just collected how many times Ramsri comes. For example, Ramsri comes 2 times, we can just say 2 by the total number of words. That's the term frequency of Ramsri. But there is another interesting semantic that we have not captured, which is the document frequency of Ramsri. What that means is that how many times does the word Ramsri occur across documents, in our case across sentences. Similarly, forget about how many times Batman comes in Batman Begins movie, but out of all the 3500 movie plots, how many times does the word Batman come? In how many movie plots does the word Batman exist? Maybe 20 movie plots? Then document frequency is simply number of times the word comes by the total number of documents. So for example, Batman could be 20 by 3500, and in this case when it comes to Ramsri, the document frequency is how many times Ramsri comes across these sentences. So we have only 2 sentences with Ramsri, 1 and 3. And how many sentences are there in total? 4. So the document frequency of Ramsri is 2 by 4, that is 0.5. And similarly, just like how we created term frequency for each document or sentence, we can create document frequency for the whole corpus. Again, you take all the unique words and all you do is, in how many document does the word occur divided by the total number of documents. That's the document frequency of each word. And the interesting thing with term frequency and document frequency is that term frequency is calculated for every document or every sentence, whereas document frequency is calculated only once per corpus or the collection of documents. So here we know that the document frequency of Ramsri is 2 by 4, 0.5. And now we have captured 2 interesting statistics. How many times a given word occurs in a document and how many times a given word occurs across documents. The first one is called as term frequency and the second one is called as document frequency. We'll see why we have IDF, that is inverse document frequency. Now if you intuitively think about it, what are the characteristics of an important word or keyword? I think it's a little bit subjective what a keyword or important word is, but what do you consider as a prime or focus word? A word is considered as important if it frequently occurs in a document, but it is rare in other documents. That means, let's say in this sentence, if Ramsri comes multiple times but it doesn't come in any other sentences, then we know that Ramsri is an important word for this sentence. Why it should be rare across documents is, even let's say simple words like and, or, is, all these things occur quite a lot of times in a given document or sentence. So the term frequency is high for even words like stop words. Now the only way to filter stop words from keywords is if you take the document frequency as well. That means is occurs in every sentence. So it is not rare, it is very common in everything. So a word is a keyword if it occurs frequently in a document, but it is rare across other documents. For example, just imagine our movie plot, Batman Begins. If the word Batman comes very often in a movie plot, that is Batman Begins, but it is very rare and occurs in maybe 10 or 15 movie plots across 3500 movie plots, then that is considered as an important word. So essentially, for a word to be important or prime or keyword, the words term frequency should be high in the document and the document frequency should be low. That is, across the documents, the presence should be rare. Simply put, a word's importance is directly proportional to term frequency. That is how frequently a word comes in a document, whereas it is inversely proportional to the document frequency. That is, the lesser the document frequency is, the more the word importance is. We can club both of these things. We can combine both of these things. If you have two directly proportional things, then you can just multiply them and add a constant. So you can simply say that a word's importance is calculated as multiplication of term frequency and inverse document frequency. So let's just understand it for the word Ramsri. You know that in the first sentence, the term frequency for the word Ramsri is 1/6, so 0.166. And the document frequency for Ramsri is actually 2/4 because it only comes in 2 sentences out of the total 4 sentences, so 0.5. And the inverse document frequency of Ramsri is just 1 divided by document frequency, that is total number of documents divided by number of documents Ramsri comes. So in this case 4 divided by 2, so 2 is the answer. So IDF of Ramsri is 2. The interesting thing to note is that term frequency is a fraction, for example 0.166, and inverse document frequency can be high even, because let's say if you take Batman Begins, maybe the word Batman only comes in 2 movie plots and there might be 10,000 movie plots in total. Then the inverse document frequency of the word Batman is actually 10,000, that is the total number of movies divided by 2, the number of movies in which Batman comes. So the number could come out to be 5,000, and if you have 1 million documents and it comes in only 10 documents, then this number becomes very high, right? And the thing is that to calculate TF-IDF, we are multiplying term frequency 0.166 with the inverse document frequency, in this case 2. Whereas for Batman Begins, it could be again a very small number term frequency multiplied by a very high number for inverse document frequency, like 5,000, 10,000 or something like that. The problem is that we are multiplying numbers in different ranges. This term frequency is a fraction and inverse document frequency is a very high number. So in order to bring inverse document frequency also into comparable range, we apply logarithm. Why do we apply logarithm? Is simply because, you know, log 1 is 0 and log 10 base 10 is 1, log 100 is 2. So even if you are exponentially increasing, the value when you apply logarithm comes out to be very small. So log 10,000 is 4. Now what happens is that instead of using inverse document frequency directly, since the value comes out to be very high, we'll just apply logarithm to it. Then you can multiply the logarithm value and term frequency directly as they are in the comparable range. So we will modify the formula of inverse document frequency as log total number of documents by number of documents in which the word comes. So in this case, inverse document frequency of Ramsri is simply log of 2, as I mentioned, that is 0.301. Now you know that term frequency and inverse document frequency of Ramsri are in the comparable range, and you can multiply them and calculate get TF-IDF. Now one thing to remember is that, let's say if Ramsri occurs in all documents, then we have log of n by n, because that is log of 1, because we have Ramsri in every documents, but log of 1 is actually 0, so the inverse document frequency of Ramsri comes out to be 0. and when you are multiplying TF IDF, because IDF is 0, it's vanished. In order to avoid that problem, what we do is we add a +1 to the inverse document frequency. Since we are just doing relative calculations, adding a +1 doesn't hurt. It will just avoid the cases that this is completely 0. And the other thing is that, let's say if the word Ramsri doesn't exist in any document, then we are dividing log n by 0. So divide by 0 error. In order to avoid that, we just add a constant +1 at the bottom. Similarly, we add +1 at the top as well. Although our initial IDF had only log 1 by document frequency, we added +1 to it and also +1 to the numerator and denominator to avoid divide by 0 error and other things. So finally, this is the equation that we are going to use, and this is the same equation that a lot of libraries use as well. So at the end of the day, the IDF of Ramsri comes out to be this, which is log 5 by 3 +1. Since we have 4 documents, we have log 4 + 1 divided by 2 documents in which Ramsri occurs, so 2 + 1, so log 5 by 3 and a +1 in total, so 1.221. Now you can get TF IDF of Ramsri as 0.166 multiplied by 1.221, so 0.203. And with this, we are able to convert every document or sentence into a vector. And how we are doing that is, first we'll collect all the unique words in the corpus, and this is the length of the vector that we are going to calculate. So in order to get the TF IDF vector for the first sentence, what we are going to do is, wherever the words of first sentence are present in all those columns, we are going to calculate TF, which is how frequent the word is within this sentence or within the document. And we have also calculated IDF. So as I mentioned, IDF is calculated only once for the whole corpus. So IDF is already pre-calculated and available. All we do is we get the value of TF for Ramsri on the fly, and we get IDF and multiply it with that and fill in the value. So now for every sentence, you get this long vector of all the unique words, and that vector is filled with TF IDF values for each corresponding column. That's about it. So sentence 1 is converted into a vector, sentence 2 is converted into a vector, similarly all the sentences. Or in our Batman Begins or movie plots case, each movie plot is converted into a vector. Now you can see that the vector is actually very long. For example, if you take movie plots, the whole corpus might have 50,000 or 70,000 unique words. So the vector, although you are creating a vector for only Batman Begins, you'll only fill the values where the words from Batman Begins are present, and rest of the columns will be completely 0. So essentially, no matter how big the plot is, you'll always have a 50,000 vector or something similar, and that vector is very sparse. That means a lot of values are 0 and only few values are filled. So that is one of the problems with TF IDF, where you have very long sparse vectors no matter how big or small your movie plot is. That is one of the shortcomings of TF IDF actually, which is solved by advanced models like sentence transformers that we'll discuss later in the later sections. So at the end of the day, for every new document, let's say if I get a completely new movie plot, what I am going to do is I am going to calculate TF for every word in that movie plot, but I have pre-calculated IDF from the corpus, and I'm just going to multiply that and get the TF IDF vector for any new movie plot. And if a new movie plot has some new words, simply I'm just gonna ignore those because I have my vector length fixed, because the vector length is fixed by number of unique words in the corpus, and I only fill those values that I need. And even if you do not understand this completely, don't worry at all. In the next section, we are going to see everything in code, and it will be very, very clear for you. Now, as I mentioned, this vector need not be just single words. Apart from single words, you can add even n-grams like Ramsri is, Mark is, or even trigrams like Ramsri is teaching, etc. So this vector could be not just unique words, but it can also be appended with unique bigrams and unique trigrams from the whole corpus. Now, if you take our movie plots, then it might grow from 50,000 to 150,000 or 200,000 all as well, if you try to add even bigrams and trigrams. But you might also gain performance in some of the use cases. Now what happens is that you can just compare two vectors with each other and kind of see the similarity and other things. And we are going to see all these things in code in the next section. Thanks for watching.